Here we go. All right, fun times today. Hope you're ready. Um, the long-awaited and aforementioned actual content on specific engineering topics is going to start today. This took a little bit more prep work than I expected, so apologies for the delay. That and the fact that there was a new World of Warcraft expansion that came out had absolutely nothing to do with it. Um, but welcome to Statics. Um, this is, as I mentioned, sort of the now that we've talked about units, we've talked about measurements, we've talked about systems of knowledge and all that good stuff. Like now we actually get to talk about engineering, right? So, um, what are statics? Well, at the end of the day, statics is defined by a specific constraint that we place on systems of forces and moments. And as you might imagine from the name, so if you'll recall, right, we had this form of Newton's second law. Uh, not quite F equals ma, but it let us look at the relationship, right, between um, the specific state of a system, etc. We have an rotational analog for this, of course, R cross F, or moments. Um, but what makes statics is we set all of these things to, I'm trying to juggle the monitor less too, so is that right here? Hopefully that's actually coming through. So the sum of all forces is equal to 0, and not just like the magnitude of those, right? So we can specifically break this out and say for a given system, all of the forces along the x component sum to 0, all of the forces along the y component, etc. And the same thing for moments about different axes. Those are a little bit trickier because we have this basically like a cross product expansion that takes place for moments, right? So if we wanted to expand this term, um, we have a magnitude representation, right? We can use the nifty cross product identity here if theta is the angle between those vectors. But if you wanted to break it out by dimension, what you'd see is the dimensions are actually coupled. So this is one of those things that makes rotational dynamics a little bit stickier, is as we're looking at how these elements decompose, you'll have different combinations of, so for the ith moment, right, y hat fz minus, like you actually have to break out the cross product, and what you end up seeing is, of course, since it's a cross product, that the elements of one dimension, as we sum these to 0, are dependent on the elements of another dimension, right? The rotation is not entirely orthogonal here. So we can set all of these things to 0, and you can imagine for the for the y, this is for the x-axis. For the y-axis, it's z fx minus da da da, right? Because you're just expanding the cross product here. We have these different constraints. It just gets a little bit more complicated because of the way that the dimensions are coupled. But at the end of the day, statics simply is a system of forces and moments that we sum to 0 in order to place constraints on that system. So basically what we're assuming is there is no acceleration within the system. It is static. And that condition, by and large, that constraint is enough for us to solve for the dynamics, or not the dynamics, the specific state of the system. What is the force here? What is the force there? What is the moment there? Etc. So if you recall, when we're talking about systems of knowledge, right, the number of constraints you have in a system has to equal the number of degrees of freedom if you want to solve for specific values in a system of equations. But that's very much applicable here. We have like say a bridge, right, or a building or something like that with a wide variety of degrees of freedom. There may be a joint here, a beam there, a pulley there, all this fun and interesting stuff. But we need to place constraints on that in order to solve for what the state of the system is. So given some static load, we may be able to come up with, okay, we have restoring forces here, and that means this force here, and that means this moment here, right? Because we're able to place static constraints on the system. Another important concept, especially when we're talking about moments, is this concept of a centroid. So with respect to rotational dynamics, right? Let's say we have a two-dimensional shape here. There is some centroid, or if we have like a one-dimensional, maybe there's a beam and it's not uniform. Maybe it's, more dense over here or something like that. Maybe there's a distribution of density. There is some centroid to this element, whether it's one-dimensional or two-dimensional, or if it's like a volume, right? That's a really poor volume, but and we have to be able to determine what the centroid of that element it is in order to characterize what those moments are. Because this R vector here is not just some arbitrary R vector. It can be, but it's typically some relative displacement. When we look at a moment of a beam, for example, like a cantilever, we're typically going to choose a point and say, okay, there's moments here, there's way here, there's a person standing on the diving board. So what's the moment that it's competing, right? This R is with respect to some point. And so for given geometries, we need to know what the centroid of those geometries is, so we have a convenient place to determine the moments of. So that centroid for like the x component of that centroid, for example, let's assume like xyz, right? Is basically just a weighted average, and there is some function that you're going to integrate over that geometry and divide by the cumulative value of that weight function, if you want to think about it, or density, or what have you. And this works across dimensions too. So the centroid, of course, is a position. So let's see, y 1 over L y dl. We're integrating with respect to the length. So you'll see exactly how that works out, but it can get a little interesting. So that's 1 over L, right? But it's identical for higher dimensions too. So if we have an area, Cx would just be 1 over ax dA, and the same for the other elements, right? It's just a weighted average over the unit of integration. For a volume, 1 over v integral of x dv, right? And the same thing for y and z as well. And we'll see exactly why this is important later on. The other rotational concept we want to cover here is this idea of a moment of inertia. So if you have a beam and it distorts, for example, right, this is no longer sort of a linear displacement. This is actually a rotational displacement. So we need to consider when things are bending or under other sorts of torsional loads, like what is the moment of inertia within that continuum, within that mass. So if we have, we'll start out by treating this sort of generically, integrated over the area, x squared, y, in the y plane, y squared, the z, warned you. Rotation's a funny beast. I'm pretending here that these are sort of unified set of relationships, right? But in reality, it's this and this. So x and y is like if you have, there's some x and y moment of inertia for torsional displacement here, if the geometry is bent. Whereas if this geometry was twisted instead, let's see if I can depict this graphically. I'm not going to be able to depict this graphically. This is going to be horrible. Oh God, yeah. So let's pretend like my artistic skills here can actually represent the twisting of a geometry. You have a polar rotation or polar distortion instead, in which case the moment of inertia for that is a polar about the sort of the axis of rotation, right? So there's displacement that you integrate across that axis of rotation. Sorry, wrong window. We have all these, very basic concepts of forces and systems, etc. How do these actually translate to things in the real world? Well, we have what are called sometimes machines or symbol machines or common mechanisms that define elementary ways in which these forces and moments and relevant boundary conditions can interact with each other. Even in a static system, these are the elements of the system you can aggregate using known laws and rules, right? So if we think about simple machines, there's a couple of useful ways that this can break down. If you have a beam, for example, a beam is typically something that exists under compressive load, although it can be under tension as well. But, so there is some force, right, that's acting upon the beam, and there's a force in some equal and opposite direction, because again, we're talking about statics here. Cables, on the other hand, will only be static under a tensive load. And within a system, some combination of these elements will be represented basically in a graph, right? These are graphs of relationships. And so the edges of that graph might be a beam or a cable or something, and then these vertices will be sometimes called a pin or a joint. And those joints represent places where these forces combine, places where we can add the forces, set them to zero across different components, and then determine, like, okay, given these relationships, what constraints help us figure out what the forces are. So those vertices of that graph are basically, as we go through a complex problem, those are the steps, going from places where we know more to places where we know less. We'll solve for the different variables and unknowns at each step, and then sometimes we'll combine them in ways where they might cancel out, or they help us figure out like a set of simultaneous equations to solve. But if beams, cables, and pins are sort of the elementary, so there are really interesting ways where you can combine these things and transform like forces and moments across each other, right? So let's consider the case of a pulley, for example. We have a pulley attached to a thing, and there's some, cable with a force here, and some cable with a force here. And in a very simple pulley system, we know that those forces are equal to one another, right? There is no magic transform happening here. But we can make this more complicated, right? You can combine pulleys, or you can, those pulleys can be, you can have a force. You can couple pulleys in systems. There are ways to play these elements in the way they transform forces off of each other, where, oh, I got that one wrong. If you couple, let's see if I can remember which one. Yep, I got that wrong. Sorry, really messing up my pulley examples here. If you couple n pulleys together, right? If you have two pulleys, 1/2, n pulleys, you can actually couple into force reduction of 1/n. Of course, there's greater displacement, right? So you'll recall this trade between what we called across and through variables when we were looking at like analogies across engineering systems, right? Basically, this is a way to trade force for displacement. You can amplify force at the cost of reduced displacement or vice versa. So it's a way for you to trade in the space when you're designing systems. And there's even ways, this is kind of crazy, to, see if I can draw this correctly. It's been a while since to have like a pulley with multiple diameters that you can then, like a differential loop, where there's some force, the outer diameter, and let's see if I can do this correctly. 1 F2, if the outer diameter is d and the inner diameter is, let's say, lowercase d, you can actually use the ratio of the diameters as a means to amplify the one force into, or transform one force into the other. You can imagine how, like, cases where one diameter approaches the other, this turns into zero, and it's like, okay, there's no point in differentiating because it's locked against itself. Or where one diameter goes to zero, you reduce to this case, right? Or where the inner diameter goes to zero. But so these are pulleys. You can see how those might be able to translate rotational dynamics into linear dynamics, or transform different scales of linear dynamics into each other. But one of the more common things that you'll see in statics is specifically looking at considerations of structures, right? So whether it's a bridge or what have you, what we will, this could be a building, this could be a diving board, this could be, many, many things, but we'll typically describe something like this as a truss. So this might be some unique, I don't know, bridge design. That's the really bad bridge example, but there's all sorts of different truss designs in the world, and if you look at, you know, railroad bridges or what have you. There we go. The different truss designs that basically shape and direct forces in different ways. So this is a little bit more complicated, but this also ends up showing us a really good example of how these systems can end up being solved. So if we have some number of members, right, for the system, so like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, there's 11 members of the system, and 1, 2, 3, 4, 5, 6, 7 joints. We can relate the degrees of freedom to the constraints in terms of when you consider, like, we're able to sum these across 3 dimensions, and each force will be acting in equal and opposite directions, right? So we can determine whether a given structure is determinant, as we call it, by comparing the number of members versus the number of joints. That's supposed to be a 3. So if the number of members is equal to the number of joints minus 3, joints basically being constraints where we can couple these relationships, right, where we can sum the relationships across 3 dimensions, then we can determine whether or not the system can actually be solved as a static system. So that's a useful equation to remember. But the problem-solving approach here is a lot more incremental than that. So let's say this is a bridge, right? So you'll have some sort of restorative force on either end, some representation of weight. Maybe that, you know, we'll place the weight here in the middle. And what you want to know is either the force borne by one of these beams, the force borne by all of these beams, and you can, like, what the greatest force is or what the torsional moment is. And you'll start at a place where there's more, you know, more things that are known, and you'll basically march through those dimensions at each of these points and determine, okay, what is the set of equations across those dimensions? How can we combine them? And then how can we use those relationships to solve the equations, sometimes simultaneously, sometimes just by, okay, solve this variable here, that variable there, so we can figure out what the unknowns are. And unknowns in this case would be like, you know, the force borne by this beam here, right? Something like that. It's typically of interest. But we're talking about very ideal systems so far, and one of the things we can't really get away with for long, even in a static system, is having no consideration of friction. Right. So let's think about different models of friction, because at the end of the day, friction is actually a really complicated thing, right? You have 2 boundaries, and those boundaries have some non-zero motion, relative motion, right? So the dynamics of that interaction is actually determined on a very, very small scale, like the relative roughness of, or the direction of the grain, the things that are very hard to capture in sort of simple macro relationships, but we try anyways. So what we try and typically do is, if you have, let's say, some, you know, classic block, right? Let's say it's on a level surface. There's some weight, and since it's a static system, the force, the ground is also applying a force back to the block. It's pushing back up, so we have some weight and some normal. The normal force is always orthogonal to the surface, even if this was like a ramp, right? The weight would be going down, but the normal force would be orthogonal. So what we would model friction as in this case is the force of friction is some coefficient times the normal force. Well, what is that coefficient? It's kind of magical, right? There's a lot of things wrapped up into the frictional coefficient. We typically use mu. But for different material interactions, we can approximate, okay, like a wheel rolling over a road have some sort of coefficient at the boundary, then we'll characterize with this value empirically determined, right? But even that within the same system and same surfaces is not necessarily constant. We might actually need different frictional coefficients to capture different behaviors. So sometimes you'll see a smaller value for this called mu sub s, or static friction. So if things are not in relative motion to each other, for example, like how much force is required to overcome the stationary resistance of friction. Or you might see static friction used to impose what's called a slip condition. So let's say there's some force acting upon the body, and we might say, well, there's some frictional resistance to that force such that if the force is less than that resistance, using like a static frictional coefficient, then it's not going to slip. As that force increases, it might approach this value, right? And at which point it starts to risk slip, or there may be impending slip. And then at some point, the force might be greater than or equal to some, you might call this like a kinetic value, where mu static is less than mu kinetic. Where it's like, okay, now we're moving, right? Like there's some loss of energy as a result of the relative motion, but there's actually a different frictional coefficient used here to capture the resistance for different conditions between the boundaries. So we're no longer just in risk of slipping, like we're actually moving, right? And actually, this might be the other way around, depending on what conditions you're concerned with or what surfaces you're talking about. With those models of friction, that's actually enough for us to start capturing a wide variety of behaviors, especially when it comes to more interesting machines. So let's consider one in particular. Let's think about like here's like a pulley, right? And there's a cable around the pulley. So there is some force here, but if we take friction into account, let's say that belt is wrapped around some angle, right? We can actually express the force needed to overcome that resistance, or the difference in forces in different directions. Like sometimes this is like the loose end and this is the taut end, right? Given some frictional coefficient at this boundary, we could say that the difference in forces, we actually model as an exponential, is exponential product of that frictional coefficient and the angle. So the more you wrap it around, and it could actually be multiple rotations, right? The more friction it will encounter. And then, of course, given the radius of the pulley in the belt, we'd then be able to say, okay, for the difference in forces is actually that what goes into the torque that's being applied to that wheel at the moment that the wheel is experiencing or applying. So we can start to model even simple things like pulleys in ways that are a little bit more interesting and a little bit more kinetic, even just with basic friction models. But even more interesting, we can take that. Let's go back to our block example, right? We have some block on a ramp. So there's some weight. There's some normal force. Excuse me. Some frictional force resisting movement. Let's take that ramp. For a static system, we know all of these things have to, sum to zero, right? Let's define a frame here that says y in this direction and x in this direction. So let's sum the forces to, some forces in x. So this is mu n, right? Minus, say, what did we say? This angle, let's call this phi. Let's say this angle is phi. So that's the same thing as this angle here. So the x component of the weight vector here is sine phi, just kidding. Sine p weight, right? That sums to zero, and then the forces in the y component, also zero, are normal, positive, minus, cosine. Wait, this is already enough where you could see we can start coming up with expressions for these relationships, right? So there's some weight and there's some applied force, and the ratio between those two is the sine of the angle and the difference. Let's take this ramp for a moment, though, and let's pretend like we can wrap that ramp around an axis with some diameter. You can probably see where this is going, right? So this ramp is going to go around an axis. That axis has some radius. And of course, this is a screw, right? So there's a screw that might be binding to surfaces or elements or what have you, but it's bearing a load. Um, and it's bearing a load by effectively applying a moment and translating that moment into using the force of friction um, about that ramp as a means to resist or bear the load. So it will have some radius, and there will be some pitch angle of these threads. We'll call that alpha. So the smaller, the smaller the alpha, the greater the more threads you need to go around. And then we'll actually model what we'll call, so we have some moment, right? There's some load that's applying that moment. And it's like an angle of angles situation where, depending on which direction it's going in, there could be some, and it's actually, the frictional coefficient, right, product of the load, the normal, is combined in an angular space, like depending on which direction, it's the inverse tangent of the frictional coefficient with that pitch angle that you use to model the resistance of the screw and the moment that it's the moment it's applying is through the material contact to bear that load P. So there's fun ways to combine these, of course. But we're not going to spend too much time on. There's one thing that we want to spend a lot of time on here in particular, and we'll say exactly what it is. But let's spend some time with sample problems first. So our first sample problem is, let's say there's some lever, and there's a fulcrum that's like 40% of the way, right? So this is some L, this is 0.4 L. If there's some guy, let's say the mass of the lever is 100 kilograms. If there's some guy who gets up on this lever and he's walking here to the right, at what point, at what displacement, let's say our random person here weighs 50 kilograms, at what point will the lever be balanced, right? So this is a basic equation. We'll choose our system. Choosing our frame is always important. In this case, we'll choose the fulcrum as the frame, x displacement to the right, positive moments is right-handed about the fulcrum. So that lets us sort of sum moments and say that, we have two moments here. There's a moment from the weight of the lever and there's a moment from the person. And based off of the way we define moments, we'll be able to ascribe signs to those, but we know the sum is 0. So there is some moment from the weight, and that's, these are, since it's balanced and level, we know we don't have to worry about sort of the angle of the cross product, it's perpendicular. There is some force from the weight, and there's some relative displacement from the weight. So that's 100 kilograms. Technically it's a weight, so it's 100 times G, right? And that's 0.1 of the length to the left. And then from the person, there is some, so notice we have a minus sign here, right? Because if it's right-handed, this moment here is going to be negative. There's some weight of the person. So I drew him in the wrong place, right? If it balances out, he's actually going to be over here. So that's a positive moment going down. Some weight of the person times the relative displacement of the person. In this case, we said he was 50 kilograms times G to get the force, times some relative displacement x times L. We know those will sum to 0, right? So we can write out 0 equals this 100 G plus, or GL rather. Oh, sorry. Let's just multiply the numbers together. So minus 100 times 0.1 minus 10 GL plus 50 GL. Obviously those will cancel out, delta X. And delta X will be 0.2 to the left, right, of the length. So it will be halfway back over here. Not too many surprises. That's probably something you could figure out instinctively, but 20% to the left of the fulcrum, right? you can see how we can use these principles to actually write out the specific statics formulation, knowing that the moment's sum to zero and solve for there. So let's consider something that's a little bit more interesting now. My son loves trains, so let's think about like a pole with train signals that's going over a train track. So those train signals are really heavy, and we'll say the first signal is halfway out from the point of this beam, and the second one's all the way out, right? So let's say these each weigh 70 kilograms. So we know their weight is applying some force. That this beam is 10 meters long. And just for shiggles, we'll assert specific precision for gravitational acceleration. So the question here is what moment has to be supported here, right, at the joint. So if this is a static system, we know, let's, again, posit our frames. So we'll say origin here, positive x to the right, positive moment right-handed about that pivot. And given that frame, we can actually go in and start. So we assume no horizontal displacement, assume horizontal displacement 0, x at the pin, moments right-handed, and the first moment from the first signal's weight we'll call M1, second one M2. So now let's express the sum of those moments. A static system, there's some restorative moment, right? Since this is static, there's the moment of the first signal's weight, there's the moment of the second signal's weight. So now we can, of course, solve for, let's say, minus F, force due to gravity, the displacement. So that's minus 70, because that moment's negative, right? In a right-handed system, that moment's going to be rotating about that point. Negative, say, 9.81 times let's say halfway, 10 meters, and that comes out to minus 301. And it probably doesn't require a lot of imagination for you to figure out that the second moment's going to be twice that, right? So given that we know this moment and that all moments must sum to zero, we can assert with a fairly high degree of confidence that the restorative moment at that joint is going to be about 903. In this case, it's Newton meters, right? Positive Newton meters about that point in the joint. So far so good. Nothing too crazy. Hopefully a lot of this makes sense so far. Let's consider a truck driving through mud. So now let's start talking about friction a little bit, right? So there is some wheel, and the powertrain is applying a moment to that wheel I actually don't know if this is realistic whatsoever. Let's see, 250 Newton meters through this specific tire. This tire has a radius of, let's say, 0.4 meters. See, that's a little bit bigger than a normal tire if I had to guess. The truck has a mass of 5,000 kilograms. So we'll just point out right now that means the weight bearing down is going to be a quarter of that, right, if it has 4 tires. So we'll say 1250 kilograms here specifically. What we want to know is what's the frictional coefficient if the slip condition is met. So recall the slip condition is where that modeling of the frictional force is equal to the force being applied. So we know the force from the moment, this is just inverting the moment equation, right, is going to be something like this. So this is what the powertrain is applying to the surface. Newtons. And then we know the frictional force at that boundary is going to be a product of the normal, right? So the normal force in this case, we're purely vertical, so it's just the mass times gravity. So there's some mu. It's a quarter of 5,000 times 9.81, and that comes out to 12,300 times mu. So If the slip condition is met, we know that the applied force is equal to the frictional resistance. And so we can set these two values equal to each other. 625 equals 12,300 mu, and say that mu is about 0.051. So we got some pretty slippery mud here. You can see the problem approach here was slightly different. We went in the opposite direction, right? Given the moment, we want to figure out the force, the counteracting forces at the boundary of the two surfaces, because friction always occurs at the boundary of two surfaces with different velocities, right? It is resisting the velocity, the relative motion of the surfaces. Okay, let's do a little bit more math now and consider, let's say, an arbitrary area defined by a function. In this case, y equals cosine of x. So this is something like this, right? So let's say this is some area and we need to compute the centroid. So there is some point in here with coordinates cx, cy that represents the centroid about which maybe tumbling or rotation may take place for this area. We have our equations. We know how to determine each of these coordinates, but the actual integration itself is not particularly straightforward. So let's start, recall cx, 1 over a, integral x dA. We don't know this and we don't know this. We want to figure those things out. So the easiest thing to do, of course, is just going to be to integrate, determine the area under the curve. In this case, this is pi over 2, right? This is 1. So if we integrate from 0 to pi over 2, cosine x dx, we'll know the area under that curve. That is sine x evaluated at pi over 2 minus sine x evaluated at 0, which is 1. Okay, so no big surprises here, right? The area is 1. But let's, we still need dA, right? Because we want to integrate with respect to an axis, x in this case. So how do we transform the inside of the integral? Well, since we're engineers, we're going to say if you computed a as a function of x, you'd integrate from 0 to x. That function cosine of x dx, which means if you differentiate both of these sides with respect to x, what you get on the left is dA dx. The integral cancels out and you have cosine x, right? So this is what's going to let us replace dA here with cosine x dx, basically. So if we want to determine the actual centroid, I should probably keep a equals 1 here, but I'll trust that we can remember something like that. Now we have the information we need to actually go through and compute the centroid for this. A equals 1. 1 over 1, the integral of x, recall dA, we determined to be cosine of x dx. This is a little bit more complicated, but it's not, particularly crazy. Cosine of x plus x sine x, and then that function evaluated at pi over 2 minus that function evaluated at 0. You can plug and chug a bunch of these. Cosine of x pi over 2 is 0. Pi over 2 sine at pi over 2 is 1, so that's pi over 2, right? Minus at 0, cosine of x is 1, so pi over 2 minus 1, and then x is 0, and 0 times whatever is 0. So you can say this is pi over 2 minus 1. But that's just the x coordinate. And believe it or not, that's the easy one, but that's mainly just a result of the geometry we've chosen here. So let's capture this over here. Pi over 2 minus 1. And now let's do the fun one. Let's see. Right, so cy has the same form. 1 over a y dA. We'll go ahead and determine dA in a similar fashion. by, let's see, if we wanted to express the area as a function of y, we would integrate this function, which of course is cosecant from 0 to y, some y value of y cosine, inverse cosine y dy. Differentiate both sides with respect to y. No big surprises, right? But now comes the spicy part where we actually have to do the integration. So 1 over a is 1 over 1. Y dA we determined was, no surprises there, dy. We integrate that from 0 to 1. And so this is where you go to Wolfram Alpha, or, ask your really good friend who happens to be a math major, like, what is the integral of this function? Because it's not particularly straightforward. I will let you in on a little secret here, since I practiced this ahead of time. That integral is something really fun in a way that only complex transcendental trig integrals can be. 2y squared cosine inverse cosine y plus inverse sine y. And then, of course, that's integrated 1, or evaluated at 1 minus evaluated. This, believe it or not, if you work out all that math, comes out to pi over 8. So our centroid for this area, the coordinates for the centroid are pi over 2 minus 1, pi over 8. Voila, right? How hard is that? That's just a little calculus. It's just a little joke. Okay, believe it or not, that was not the most fun or spicy or interesting problem. So now we're actually going to talk about, statics in the traditional sense of structures. So let's consider a bridge. It's not a particularly complicated truss, but it is a truss. So points A, B, C, D, E. So that bridge is going to have some sort of mass. Therefore, it's going to be bearing a load. Let's model that with a weight here at the centroid. Believe it or not, these are symmetrical. It may be hard to believe. What's more, let's assert here that, wow, that's a really bad drawing for this assumption, isn't it? Screw it. Let's redraw this. We could probably redo it if we wanted to, but so there's some length here, there is some length here, and then there's some length here. This I didn't see. That one, that one, that one, that one. It's different distance, same as that one, different distance. What we're trying to get here is just this assertion that this is 45 degrees, or pi over 4, right? So this length and this length are the same thing. Again, A, B, C, D, E, with some restorative force here, some, at where the bridge is being held up, sort of force here, and a weight. So what do we want to know? Well, first let's, we said this is 1,000 or 10,000? 10,000 newtons, right? So what are the restorative forces? You can probably look at this and figure out, but let's walk through the math as a means to sort of warm up here. So let's consider this point here. And specifically, let's consider the moment about this point here. So we know there are certain forces acting upon this system with respect to that joint. We know there's a force down and there's a force. So let's define, in addition to that origin, the positive moments are going to be right-handed about that point. And that, let's say M at A, we know that's going to sum to 0. So this first moment is, let's say this is 1 meter. I think we said it was 1 meter in our, yes, this is 1 meter. So that's 1 meter R times, it's going to be negative because it's right-handed positive, 10,000 plus distance of 2 times R2. No real surprises here. that R2 is going to be 5,000 newtons, right? And then you can do the same thing from R2 because we want to determine, let's just write this out. We want to know the restorative forces, we want to know the force at beam AB, and we want to know the force at beam D, borne by beam DE. So you can either look at the overall, the sum of these forces has to equal the sum of that force, and you can say, yeah, that's going to be 5,000 newtons as well. Or you could sum the moment from here. But that's not the interesting part, right? The interesting part are these third and fourth values here. So let's just make sure we know. So this is the meat and potatoes of this section, is how do you actually solve a statics problem? Well, first we'll consider the point A, right? So let's construct a free body diagram at point A. There's a restorative force. There's some force, we'll call this AB, and there's some force AD. Notice we're making some assumptions here. We're assuming that all the forces of the beams are acting, against the point. If we see some negative signs, we'll know that that's, they're actually tensive forces instead of compressive forces. But this is enough for us to say, given point A, let's see, the force in the x dimension about point A is, we know these are all the same angles, 45 degrees, so that's FAD. Let's see, from our frame, positive to the right, those are both going to be negative. Sine pi over 2 minus FAB. And forces in the y direction about A are going to be positive R1 minus FAD sine pi over 2. And we already have enough, and of course these are all equal to 0, right? We already have enough to start observing, like, okay, if this is a known quantity and this sums to 0, that means that this is a known quantity. If this is a known quantity, and we know this sums to 0, that is a known quantity, right? So FAB here is actually something we can solve without looking at any other points, just purely from these constraints. So if let's see, 0 equals R1 was 5,000 minus FAD, sine of pi over 2 is root 2 over 2, right? We know FAD is going to be equal to root 2 times 5,000. Now we can go in here, FAD, right, is equal to that. Sine of pi over 2 root 2 is just going to be FAB is going to be root 2 times root 2 times 5,000. It's just going to be 10,000 newtons. Happens to be the same, force that the truss overall was bearing. So we know this, we know this, we know this. Let's go ahead and write that out here before we move on to, let's see, B. Also, let me make sure I got the signs right here. 0 minus, okay, so FAD is acting in that direction. FAB, that's negative. Let's see, it's actually going to be negative. So it's actually in the opposite direction, right? So that's something we'll want to consider, keep in mind. FAB is acting in that direction, right? So we're using a convention here where FAB means the force applied to F from B. So FBA would be in the opposite direction, right, when we're considering the forces about point B. But as it turns out, we can just look at, here, I'll jump to the end here. I think I can do this. Hey, I can do that. That's much easier. Okay, so let's move on to the next point. We could do B next, but we're going to skip straight to D. So if we consider the point at D, there will be some force D applied from A. There will be some force against D applied from B, and there will be some force D applied from E, right? Those are the three forces, and there's no moments, these are joints. So let's go ahead and sum those forces. F in the x direction at D is equal to 0. That's equal to minus FDE from our convention here, plus FDA sine stuff pi over 4, minus FDB sine pi over 4. And then in the y component, actually, sine. This is cosine. But fortunately, it's the same thing. My mistake. Cosine, not sine. Let's see. Y force is about D. So F D A. Now it's sine pi over 4. Let's see. With our convention, F D B sine pi over 4. Right. So we know AB. I'm trying to remember if there's some symmetry shortcut I used here. Let's see, B, D. We want to know this. We know DA from our previous. I should have written that one down. Let's see, DA, that means we know DB. And if we know DB and DA, we know what force DE is, right? So we just need to solve for those values. So in this case, let's find, so given FDA, we know FAD, we know FBD. These are the same products, so we know that they're going to be equal and opposite. So we said FE, I'm gonna get my letters mixed up here. Okay, FAD was root 2 times 5,000. AB, I shouldn't have written, I shouldn't have erased all the things that I was writing down. Good thing I kept a reference over here. All right. Let's actually go through this. Okay, F A B F A D B was, let's see, that was A B A D was going to be, we said in that convention it was going to be minus 5,000 newtons. So if when we summed in the y direction we had FAD sine stuff, we're going to divide by sine stuff because that was the same thing, plus FBD. So we know FBD is also 5,000. And that means when we summed in the x direction, we said FAD root 2 over 2 minus FBD root 2 over 2 minus FDE. So we know this, this is the same but opposite signs. So we know FDE, see, root 2 over 2 will pull out 5,000 plus 5,000 is 10,000, right? And that just works out to root 2, 5,000. Does that agree with what I computed? Let's see, sine, that's 2. 10,000. No, that's just root 2. So it's 10,000 root 2. 10,000. No, sorry, root 2, 5,000. Square root of 2 times square root of 2 is 2. That's 10,000. Wow. You can tell it's too long since I did manual math and physics. So the load borne by this beam is actually equal, as it turns out, to the weight of the bridge as a whole. So Now we have our Ferrand nodes. Um, that's a lot, isn't it? I'm not even going to bother looking at how much time has passed. The important thing about that problem is sort of this chapter as a whole, in addition to how forces and moments are defined and interrelated, is this idea of, again, degrees of constraint or degrees of freedom and constraints, right? So you know some stuff here. You can constrain those relationships and start combining them to solve for the things you don't know. And if it's a determinate system, you have some guarantees that eventually you'll be able to know anything you want about that system. And that's true for trusses. That's true for arbitrary combinations of pulleys and tires and screws and frictional belts. Like forces and moments and displacements and angles, all of those things just combine into the equations of the system that you constrain with a static constraint to sum all of them to zero and then solve for the individual elements. Other important topics with this idea of machines, right? That we have these simple machines we can combine to transform between forces and displacements and moments. And then just keep in mind that those models of friction we had were very simplistic. They represent a very complex phenomenon, but they're useful ways to capture the behavior of friction in real systems that describe the function of things like screws and belts and pulleys in a way that lets us fit them into the larger model of the system as a whole. So still very useful. A lot of stuff we need to get to this week, but this was enough for statics, believe it or not. Next section of the engineering content will be specific to dynamics, surprise, surprise, so we can actually start considering time within our systems, which should be a little bit more interesting. Certainly no shortage of math here. I mean, we did almost an hour of scribbling equations and trigs, but it's really the problem-solving process that you should be taking away from this, because it's the problem-solving process you're going to be able to apply to much, much more complicated systems as well. Take care. See you next time.